Hello and welcome everyone. This is Noah, and in this video we're going to look at an application of factoring trinomials. The example we're going to use is that of a ball being thrown off a building 200 feet above the ground. Its initial vertical velocity is 40 feet per second. The downward acceleration of gravity is negative 32 feet per second squared, the negative indicating that gravity is pulling the ball downward. The height of the ball can be modeled then by capital H of t equals negative 16t squared plus 40t plus 200, where t is time in seconds and capital H is the height in feet. We want to answer the following questions about this. Get a graph. We're going to find the vertex, find the vertical intercept and its mirror point. We're going to find the horizontal intercepts. We're going to get a graph. And then we're going to answer a couple of questions, like how long is the ball in the air, how long is the ball going up, and how long is it going down? What's the domain and range of the function h in context of this scenario? Let's take a look at a couple of things before we get too far in here. The ball is being thrown off of a building 200 feet above the ground. So its initial height is already 200 feet above the ground, and we can see that in the equation with that plus 200 right there. Its initial vertical velocity is 40 feet per second, and that's also found in the function here, the b value, 40t. So these numbers, that's not coincidence. We're not going to look at how to build this function today. We're just going to say if we're given the function, then can we answer these questions? There is one other thing to note about this, though. The negative 32, the acceleration of gravity, which is constant near the surface of the Earth, that does relate to that negative 16 in front there. The negative 16 is half of that. There's a reason why all of those numbers are what they are and why they go in the locations that they do, but we're not going to get into that today. That is something that you would look at in some more advanced classes here. So what we want to do is just analyze this function and make some sense out of it, get a graph, and come to understand some facts about how the ball is moving in time and what its heights are in time. So the ball is starting at 200 feet and it's going upward, and then it's going to come back down and it's going to pass the edge of the building and continue down towards the ground. It has a maximum height though, right? It's not going to go up for forever, and that maximum height is going to be found at the vertex. What is the vertex of this function? So the t value of the vertex is going to be negative 40 over 2 times negative 16. This is going to give us 40 over 32. This reduces 20 over 16, 10 over 8, 5 over 4, or 1 1/4. I'm not sure how much I want to be doing this arithmetic. If I do h of 5/4, this is going to be negative 16 times 5/4 squared plus 40 times 5/4 plus 200. Let's go ahead and just use calculator for this. Oh, this is a different problem. Do negative 16 times 5/4 to the second. To the second. We go plus 40 times 5/4, and then plus 200 gives us 225. This equals 225. So the vertex is going to be the point 1 1/4, comma 225. This is saying, put this a little higher. So this is saying 1.25 seconds into the flight, the ball has a maximum height of 225 feet. Let's go ahead and put that on a graph. Just start graphing as we go here. Get a vertical axis. I'm going to give myself plenty of space here. I need to get to 225 feet high. My horizontal axis is t, time in seconds. My vertical axis is capital H, height in feet. We want to get a maximum height of 225. So let's see, let's actually move this horizontal axis down a bit more. If I put 200 here, I go down 1, 2, 3, 4, 5, and make this 150. Or no, if I do these by 4s, that's what I was thinking, 25 each. Then this is 100. My 225 would be right there. And then another 4 more down, this would be our 0. Okay, so actually, yeah, I can move this up. T in seconds. Okay, so I've got 1 1/4 seconds in. Let's do 1 second, 2 seconds, 3 seconds, 4 seconds would be out here. That way I can get quarters in here. So at 1 1/4 second, we have a maximum height of 225. 1 1/4. Get a maximum height of 225. Okay, part B. It says, what is the vertical intercept of capital H and its mirror point? So I'll say, what is h of 0 to get the vertical intercept? That's going to be 200 when I plug 0 in for t. It's the point 0, 200, and that's just indicating the ball starts (200) feet up, and we saw that in the original explanation of the problem as well. So we can mark that point. Now its mirror is going to be over the axis of symmetry. If I move, we had 1 1/4, if I do another 1 1/4, it's going to put us to this point. This is at 2.5 seconds. That's a fraction. 2.5, comma 200. So if the ball starts at 200 feet, it goes up to 225, and then it's coming back down. And it hits the 200 feet mark at 2.5 seconds in here. So 2.5, comma 200. So the ball comes back down to 200 feet, 2.5 seconds into its flight. We can see that this should continue coming down and eventually hit that t-axis over there. I might need to extend that out a little bit. Let's see exactly where it's going to hit. So if I set the height to 0 to find the horizontal intercepts, I'll go 0 equals -16 t squared plus 40t plus 200. And we can factor out a -8 here. So if we look at 16, 40, and 200, 8 goes into all of them. So I'll have, and I want to pull out that negative from the front. So -8 times 2t squared minus 5t, and then 8 goes into 200, divide it by 2 3 times. It'll be 100, then 50, then 25. And it's negative because we factored out a negative. Now, with this product, we can really just divide out that -8 and say 0 just equals 2t squared minus 5t minus 25. And what we've been learning is how to factor these. So I'm going to use the AC method. And that's going to be 2 times -25 equals -50. And I want to find two factors that multiply to be -50 and add to be -5. So I think a +5 and a -10 will work. So I'm going to break this up as 2t squared plus 5t minus 10t minus 25 and do some grouping. If I group the first two and then the second two, we'll get 0 equals t times 2t plus 5, and then minus 5 times 2t plus 5. By factoring out the greatest common factor from both, I can then pull the 2t plus 5 out to be left with t minus 5. And so from this we get t equals -5 halves, or t equals 5. So our horizontal intercepts are going to be at 5, 0, and that's the only one we're going to use. So because the negative time, that's before we threw the ball, so that's not really going to count in this scenario. So this is saying 5 seconds into the flight, into its flight, the ball hits the ground. It has a height of 0. So I do need to extend this graph out just a bit here. So this is going to come out and hit at that 5-second mark. All right, that's nice. So we can see a flight path of the ball in time. So keep in mind, this is not horizontal distance. That's not being accounted for in this problem at all. We're not looking at that in any manner. We're only looking at this as the height of the ball. Okay, cool. So we've done some nice analysis. We have a nice graph. We know a lot of things about this scenario already, and we're just going to answer a few more questions. Like, how long is the ball in the air? Well, we can see that it hits the ground at 5 seconds. So it's the ball is in the air for 5 seconds total. Next question, how long is the ball going up and how long is the ball falling? So it's going up for just that first section until it hits the vertex. So it's going up here, and then it goes down for the rest of the flight path. So down over here. And the question is how long? So how much time is it going up and how much time is it going down? The ball rises or goes up for 1.25 seconds and then falls for the duration. So that's going to be from 1 1/4 to 5 seconds. That's going to be 3 3/4 seconds, so 3.75 seconds. And then last question, what's the domain and range of this function in context? Well, the domain is the t-values. In context of the problem, we only care about the t-values from when t is 0 we first throw the ball, and when t is 5, when the ball hits the ground. The range is the heights, the outputs of this function, all the possible heights that the ball could obtain. The minimum height that this ball could obtain is 0 feet high. That's when it hits the ground at the end. And the maximum height it obtains is 225 feet. And it does, in fact, hit all of the other heights in there. We can see that the heights between 200 and 225 are reached twice, once on the way up and once on the way down. But we don't need to indicate that for the range. We're just saying, what are all of the possible heights that we could get out of this? And that's all of them. All right. Yeah, so this is us taking a physical situation, the height of a ball measured in time, and looking at, analyzing that as a quadratic function that we can factor, that we can graph, and determine a lot of different information about that ball's maximum height, how long it's going up, how long it's going down, how long it's in the air overall. And we could, really indicate from this, what the ball's height is after so many seconds as we choose. All right, that's it for this problem. Go ahead and look at the Now You Try problem that comes next and give that a shot. We'll walk through that solution in the next video. Thanks so much for watching.